Imagine a scenario where you sit across a TV in your living room and assume that the light reflected from your face creates a shadow of the TV screen on a blank wall. Do you think it's possible to extract the biometric information of you from the shadows of such occluding objects? In this work, to investigate the biometric information leakage, we study the problem of inferring a person's identity from shadows. We show that the identity leakage phenomenon can be significant via maximum likelihood analysis. We show that existing learning tools can be used to achieve the predicted accuracies in real settings. In our maximum likelihood analysis, we simulate a representative scene with a linear observation model. For each identity, we compute the underlying statistics of its respective observations. For each test example, we employ a maximum likelihood rule, assuming Gaussian observations. In our analysis, we sample 16 faces from a synthetic face model with varying textures. We render these faces under different expressions, head poses, and lighting conditions. Then we simulate shadow images using the convolutional model of occlusion. Here we illustrate classification accuracies with respect to numbers of identities and signal-to-noise ratios. We observe high accuracies at moderate to high SNR levels, suggesting that shadows might be used to reliably distinguish identities from each other. Motivated by our findings, we develop a learning-based method that can be used to distinguish identities in practice. First, we build synthetic scenes composed of 3D face models, obtained from a single photo of each identity. Then we transfer what we learn from this data to the real data, without using any labeled examples. For each identity of interest, we obtain 3D models of their faces from only a single photograph by relying on a 3D face reconstruction network. In our synthetic data collection, we construct these synthetic scenes consisting of 3D face models, a blank wall, and an occluding object. In real settings, we follow a similar scene configuration. In our synthetic data, we change the head poses, facial expressions, and lighting conditions, and we use different chair models as occluding objects. Then we render the shadows of these objects using graphics software. In real settings, we collect images of shadows using an ordinary digital camera. In our method, we first train a neural network on the source domain. Then we feed unlabeled real examples through this network to perform domain adaptation. Here we illustrate feature distributions of the test data in 2D. Before the domain adaptation, the network trained on the synthetic data produces two different clusters for the source and target domains. If we look at the class labels and predictions, we observe that the network is able to perform well on the source domain, but it performs poorly on a target domain. To perform domain adaptation, we rely on aligning the feature distributions of the source and target domains. The updated network achieves over 75% accuracy on the target domain. To illustrate which portions of the shadows have more influence on the predictions, we employ a method called integrated gradients. Note that these regions typically cover penumbrae portions of the shadows, formed by the edges of the occluder. In summary, we show that it is possible to infer biometric information of individuals from indirect cast shadows using existing learning tools. Our results suggest that the primary source of the information leakage is the penumbra portions of the shadows. Our findings make a case for further investigation of the risks and an exploration of approaches to their mitigation.